Hello everyone, and welcome to my channel. This is an educational channel. We tend to focus on some great theories of everything that you might not have heard of before, things that can inspire you, help you move your paradigm, shift your paradigm, adapt to 5D consciousness, and help you with your holistic worldview. Today is our 435th video on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an American engineer, lived in the 20th century. Around 1959, he proposed his two fundamental postulates about how he had felt that the universe operated, and then subsequently he took those two postulates and put them through a process of deduction, an if this then that type of approach, and arrived at his theoretical universe. So this was his universe about how the universe would look if his postulates were correct. And then he wrote some books comparing his theoretical universe with the measured universe of the scientists that they had compiled in their tables, scientific tables, especially in this case relating to chemistry. We're looking at Larson's 1987 book called Basic Properties of Matter. And he goes through many of the basic properties of matter, such as the melting point and the specific heat. And today we're again looking at the compressibility. And he arrives at equations for these different values. In many cases, he has to come up with several equations depending on different circumstances, temperatures, and crystal structures, and various anomalies in the periodic table. But he comes up with formulas or equations, and then he arrives at his values for these basic properties and then compares them with the scientific tables. Now, most of the damage, so to speak, of Larson's reciprocal system is done in the first postulate of two, and but I suppose I can just recite them both. The first postulate is that now this is what Larson calls his universe of motion. The universe is made not out of matter, not out of energy or anything else, but it's made out of motion. And then motion is the relationship between space and time. That is a reciprocal relationship. That's why it's called the reciprocal system of theory. It's a theory, a system of theory, not just a theory, meaning that you can apply it to any subject that you'd like to apply it to as well. It's a whole, theory of everything, or grand unified theory. It works on any subject. You just have to figure out how to plug it in. But the first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And the second postulate, which we probably won't get into too much here, and which I must say I disagree with certain aspects of it, and other people have beaten me to that punch, is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Okay, now let's try to unpack that first postulate a little bit before we start this chemistry reading. The universe is composed entirely of one component, motion, existing in 3 dimensions. What does he mean by 3 dimensions of motion? Well, when Larson is referring to motion, he's really referring to what he calls a scalar motion. And a scalar motion differs from the normal motions that you might be more familiar with in that it has no direction. A scalar motion is a motion that has a magnitude but has no specific direction. Or really the direction is either in or out. You can measure or you can envision a scalar motion. If you take a balloon and you put some dots on it with a magic marker, you blow up the balloon, all of the dots will be moving away from each other. And they won't be moving in any specific direction. Every dot will be moving away from every other dot. And in fact, even the spaces between the dots will be moving away from each other. So every spot on the surface of that balloon will be moving away from every other spot or location. And that is an outward scalar motion. Now, if you contract the balloon and then all the dots will be moving toward each other, that is an inward scalar motion. These motions inherently are directionless, but you can impute a direction if you choose arbitrarily to assign one of the dots as motionless. If you say one of these dots is motionless, then you can start determining distant directions. And it appears as if there's are force fields involved with that inward motion. So that outward motion is what Larson calls the progression, and the inward motion is analogous to gravitation. Now, when he's talking about 3 dimensions of motion, what we just kind of described there, that requires 3 dimensions of space and like coordinate space. XYZ coordinates, basically it requires 3 dimensions of space to define a 1-dimensional scalar motion. So that motion is only 1 dimension. Really, the 3rd dimension would be coming of space would come if you filled in the balloon. So instead of envisioning a balloon with dots on it, you would envision something like raisin bread, where when you put it in the oven and it rises, all of the raisins will be moving away from each other. That's maybe a closer analogy to the 3-dimensionality of that motion in space. So you need 3 dimensions of space to describe 1 dimension of scalar motion, but we have 3 dimensions of that motion. So there's 3 dimensions of that scalar motion just described. That'll come into play a little bit later, but we'll move on to the second prong. So the universe is composed of motion. Motion is the relationship between space and time. I'm sorry, that's my version. Larson's version is the universe is composed entirely of motion existing in 3 dimensions in discrete units and with 2 reciprocal aspects, space and time. So discrete units, space, time, and motion all come only in discrete units. They are quantized. There's a minimum unit of space that you have to have space. There's a minimum unit of time that you have to have time. And same with motion. If you have exactly 1 unit of space in 1 unit of time, you have what Larson calls the speed of light, or what is the speed of light, what Larson calls unit speed. 1/1 = 1. And so this unit speed is the speed of the progression. So that outward motion of the balloon is at 1 unit of space per 1 unit of time, better known as the speed of light. So now, if you have a universe composed of motion, there's a few obstacles mentally that you have to get over. And the first is that you have to be able to conceive of a universe where motion precedes anything moving. So you have to be able to conceive of a universe with motion without anything moving. And that is here this what Larson calls the progression of the natural reference system. Motion outward in all directions at the speed of light. That is the empty universe of Larson, or the 0 point, the null point, the neutral point. Again, the progression of the natural reference system, or even the ether, the origin. This is the source of everything else that comes into the universe, is this progression outward at the speed of light, and this is the 0 point. This means that half the universe is moving faster than the speed of light, and half is moving slower. The half that's moving faster, Larson calls the cosmic sector, and that is pretty much unknown to science, at least in that form. And then the half that we're more familiar with is what he calls the material sector. And in the material sector, we see our normal relations of coordinate space, Euclidean geometry, 3 dimensions of space in a still frame, and we see what he calls clock time. The clock is always getting later and later and later, moving forward, or the flow of time, the progression of time. So we see in our space-anchored reference system, we see 3 dimensions of space in a still frame, and we see a scalar progression of time. So coordinate space, vector space, and progressing time. But if we were in the cosmic sector, we would see the inverse of that. We would see 3 dimensions of time, coordinate time, and clock space. Space is always getting later and later, or actually space is always getting farther and farther and farther apart, like on the surface of an expanding balloon. So you can see the reciprocal relation there. And that kind of takes us to the third prong, with 2 reciprocal aspects, space and time. Now, this is another conceptual hurdle. For thousands of years that we've thought of the universe as existing in this still space framework, and events unfolding through time. Like, so space and time are the background of the universe. And, you know, we see this 3-dimensional spatial stillness, and then the events unfold in time, this progression of time. That is what you would call the container viewpoint. But in Larson's system, space and time are not the container of the universe. They are, in fact, the contents of the universe. The universe is made out of space and time. But Larson proposes that space and time are the 2 reciprocal aspects of motion. So in Larson's system, motion is a fraction with space or time as the numerator and time or space as the denominator. And you can see this if you look at kind of the most basic kind of motion that we know of, speed. The bicycle is moving 10 miles per hour, 10 miles of space in 1 hour of time. Space over time equals speed. Or 1 unit of space in 1 unit of time. It's the speed of light. But in this example, we have 10 miles of space in 1 hour of time, space over time. And if we decided to double the speed, then we would have the bicycle is moving 20 miles an hour now. But equivalently, we could also say the bicycle is now moving 10 miles per half hour. So you can multiply the space by 2, or you can divide the time by 2. Either way gives you an equivalent statement, and that shows the reciprocal nature of at least speed as far as motion is concerned. Now, Larson spreads this out to generalize it as really all scientific phenomena are motions, and they are all reciprocal relationships between space or time. So in Larson, and again, space and time can have 3 dimensions. So you can have, space over time to the second power, or time over space to the second power, or space to the third power over time, or, any type of permutations between space and time, with either one being the numerator and then the other being the denominator. So in Larson's system, energy, matter, force, acceleration, momentum, power, pressure, these are all motions, and they all have their own space-time coordinates, so to speak. Okay, now, out of all that, the progression is the source, and then matter comes into play by kind of turning around that progression. The progression is moving outward in all directions, and there are 3 dimensions of it. And the 3 dimensions are independent, but they're generally additive. But you don't really get to the first, to the second or third one until you get through the first one. So the first one is enough to describe 3 dimensions of space and also 3 dimensions of time. Well, no, 3 dimensions of space for one, and 3 dimensions of time for another. So each one of them requires just one scalar dimension. And so atoms come about by first stilling that motion outward, that outward motion of that expanding balloon, and then eventually rotating it backwards, kind of like tying knots. And it has to be rotated in 3 dimensions. So in Larson's system, an atom is a 3-dimensional configuration. He has 3 numbers in his periodic table. So for example, oxygen, element number 8, in Larson's system is 2 primary 2-dimensional rotations, 2 secondary 2-dimensional rotations, and then 2 negative 1-dimensional rotations in the opposite direction. So every element in the periodic table has a 3-number configuration. He uses these numbers to plug into various equations that he has here for the various basic properties of matter. And for compressibility, he uses that. Now, also, there's another aspect of the discrete unit postulate that I didn't mention, and that is you got that unit speed boundary across which the rules reverse. So in the material sector, you have coordinate space and clock time, but once you cross that boundary and you move into the cosmic sector, then you have coordinate time and clock space. But within each one of those sectors, there is an inside region that where you are dealing with relations in less than 1 unit of space or less than 1 unit of time. When you don't have a full unit of space, such as an atomic interaction or a molecular interaction, then you don't have space. You only have time, because the universe is composed of space and time, motion. And so it's got to be one or the other or both. And so if it's not space, it has to be time. Larson refers to this as the time region. And in this region, this is where these atoms and molecules interact. And when you cross that unit space boundary and you move into the time region, you have to invert the rules again. And the progression is now inward and gravitation is now outward. And the same is true in the in the cosmic sector. Inside a unit of time, you have the space region. And again, the rules invert across that unit time boundary, and then the progression is inward and gravitation is outward. So gravitation is the progression is actually responsible for things like the cohesion of solids, and it is also responsible for compression, or at least the internal aspect of progression, so of compression. So when he's talking about compressibility here in this chapter, he refers to that as P sub 0, the initial pressure. And then that can be added to that can be an external pressure, which is, a physical pressure where you're forcing things closer together. But before you even get to that, you have the internal pressure. And then Larson also has to account for the rate of change of the volume of an element or a compound. And so that has to do with what he calls compressibility, the rate of compression. Okay, we're just going to start reading here and see how many other questions come up. In addition to the changes of this type, commonly called second-order transitions, that's a type of crystal structure, where the crystal structure makes an adjustment, then that also alters the compression relations. Some solid substances undergo first-order transitions in which there is a modification of the crystal structure and a volume discontinuity at the transition point, which he discussed yesterday. The effective internal pressure generally changes during a transition of this kind, and the resulting volumetric pattern is similar to the potassium chloride from the earlier figure. With the exception of some values which are rather erratic and of questionable validity, all of Bridgman's results follow one of these three patterns of some combination of them. The antimony curve in Figure 1D illustrates one of the combination patterns. Here, a second-order transition between 30 and 40,000 kilograms per square centimeter is followed by a first-order transition at a higher pressure. The numerical values corresponding to these curves are given in the tables that follow. So in Larson's system, compressibility is basically like a curve. It's really line segments. So if you're comparing the rate of compression, it might be on this slope here until you get to a transition where there are more compression factors that from the periodic table that are involved, because the compression is two-dimensional, whereas the atom is three-dimensional. So the compression is only on a cross-section of the actual substance. And so depending on how strong the compression is, more and more of the atom is involved in kind of resisting that pressure. And so that is what he calls a second-order transition. The first-order transition is when the actual crystal structure is adjusted. And the crystal structure he went over when he was talking about the interatomic distance in the chapters 2 and 3. And that has to do with the kind of arrangement of the various atoms in closest packing in the solid state. Larson believes, one of Larson's earliest books is called The Case Against the Nuclear Atom. Larson does not believe that an atom has a nucleus. Or, in fact, Larson believes that the nucleus is the entire atom. And the space that we attribute to the electron cloud is not part of the atom. It's actually the distance between atoms. So whereas the legacy scientists say that the interatomic, that in the solid state the atoms are in contact, Larson believes that they have reached an equilibrium, which is reflected in the crystal structure. But that crystal structure can change depending upon the atom, and that is what he calls a first-order transition. So when these different solids, when they undergo these different transitions, that causes the curve of compressibility to shift in direction. Okay. The experimental second-order curves are smooth and regular, indicating that the transition process takes place freely when the appropriate pressure is reached. The first-order transitions, on the other hand, show considerable irregularity, and the experimental results suggest that in many substances, the structural changes at the transition points are subject to a variable amount of delay due to internal conditions in the solid aggregate in these substances. The transition does not take place at a well-defined pressure, but somewhere within a relatively broad transition zone. And the exact course of the transition may vary considerably between one series of measurements and another. Furthermore, there are many substances which appear to experience similar delays in achieving volumetric equilibrium, even where no transitions take place. The compression curve suggests that a number of the reported transitions are actually volume adjustments, which merely reflect delayed response to the pressure applied earlier. For example, in the barium curve, based on Bridgman's results, there are presumably two transitions, one between 20 and 25,000 kilograms per square centimeter, which I believe is about the same as 25,000 atmospheres. And the other between 60,000 and 70,000 kilograms per square centimeter. Yet the experimental volumes at 60,000 at 100,000 are both very close to the values calculated on the basis of a single straight line relation. It is quite probable, therefore, that this element actually follows one linear relation at least up to the vicinity of 100,000 kilograms per square centimeter. The deviations from the theoretical curves that are found in the experimental volumes of substances with relatively high melting points are generally within the experimental error range. And those larger deviations that do make their appearance can, in most cases, be explained on the foregoing basis. The compression curves for substances with low melting points show systematic deviations from linearity at the lower pressures, but this is a normal pattern of behavior resulting from the proximity of the change of state. As will be brought out in detail in our examination of the liquid state, the physical state of matter is basically a property of the individual atom or molecule. The state of the aggregate merely reflects the state of the majority of the individual constituents. Now, that's an important point that will come into play later as far as the state of matter, a liquid, a solid, a vapor, a gas. These have to do with the property of the individual atoms, but the state of the aggregate merely reflects the state of the majority of its individual constituents. Consequently, a solid aggregate at any temperature near the melting point contains a specific proportion of liquid molecules. Since the volume of a liquid molecule differs from that of a solid molecule, the volume of the aggregate is modified accordingly. The amount of the volume deviation in each case can be calculated by methods that will be described in the subsequent discussion on the liquid-volume relations. Table 15 compares the results of the application of the first compression equation with Bridgman's measurements on some of the elements that maintain the same internal pressure all the way up to his pressure limit of 100,000. In many cases, he made several series measurements on the same element. Most of these results agree within about 3 parts per 1,000. And it does not appear that listing all of the individual values in the tabulations would serve any useful purpose. The values given in Table 15 and in the similar tables that follow are those obtained in experiments that were carried to the full 100,000 kilogram per square centimeter pressure level, where the high pressure measurements were started at some elevated pressure or where the measurement interval was greater than usual. The gaps have been filled from the results of other Bridgman experiments. Okay, so now we take a look at Table 15, and we will do that tomorrow. Now, I know this stuff is kind of ridiculously in the weeds, and you may not be understanding any of it. I'd like to read it just to kind of give you a flavor of what Larson's talking about and listen to his overall theory and how it contrasts with legacy theory. But, you know, what you want to really just get is the main points. And now these are a lot of finer points. But, you know, I just want to give you the kind of the flavor of some of the finer points. But if you can just kind of grasp the main points that I discussed before we started the reading, you know, then you'll start making progress. And then you can kind of glean a little bit at a time when you know, go into the reading. And, you know, we're moving really, really slow, but you know, I just want to read this into the record so that if a person is really studious, that they can get it. Okay, thanks for tuning in today, and we'll be back tomorrow to continue with this chapter. Have a great